Okay, so here's some background considerations for our trip to the power plant. We're going to be introduced here to the Rankine cycle, and the Rankine cycle involves, and all of thermal power involves using steam as a working fluid. So we've mostly been focusing up here with gases, and you can see there's a nice isotherm. But of course, as you get down to lower temperatures, eventually gases change to liquids and liquids change to solids. And this is the phase surface for water. And the steam power process is going to be happening here on this sort of inverted parabola shaped transition from a liquid to a vapor or a gas. And here's the mixed phase region right here. Okay, so this is where we're going to be operating. Now, the components of a thermal power plant, and by thermal power, it can be burning coal, using nuclear reactions, burning natural gas, or in our case, burning garbage. They all work basically the same. You pump up the pressure, you feed it through a boiler where it gets really hot, and the pressure goes up. It then pushes on turbine blades and makes electricity, and then it's condensed back to water. So, in very rough terms, you pump up the water pressure, you convert it to steam. The steam pushes on the turbine blades, makes electricity, then the steam's condensed back to water. Those are the four components of thermal power. Now, we're going to represent that steam cycle on a PV drawing here. Come on, you. PV. Hang on, let me fix this. So there on business, this is the PV plane. Now, when there's a phase transition happening, the isotherms are actually nice straight lines. So there's also constant pressure. So isotherms are isobars in the mixed phase region, lines of nice constant pressure. Now, since pump compression and steam expansion through the turbine happen very quickly, so when we pump up the pressure, it's actually an adiabatic process, so that's the pump. Then we're going to absorb a bunch of energy in the boiler as we change from a liquid to a vapor. Then we will pass that high pressure steam through a turbine and extract some energy from it. Let the gas do work on the turbine. And then we will condense the vapor back into a liquid, and then we'll start again. So these, remember, are isotherms. So we have two isotherms and two adiabats. Now, of course, adiabatic processes that we've seen are constant entropy processes, and isotherms are constant temperature processes. So with two adiabats and two isotherms, this looks a little weird because isotherms for a gas are hyperbolas, but these are indeed constant temperature processes in the mixed phase region. But we've already seen a cycle with two isotherms and two adiabats. This is actually a Carnot cycle. Now, on a temperature entropy diagram, it'll look a little better. So let's start with first the isotherm, then the turbine is a constant entropy process. It's adiabatic, happens very quickly. Then we go through the condenser, and then we pump up the pressure again. So this is a temperature entropy plot. It's a TS diagram. And so this was the pump. This is going through the very hot boiler. Sorry, typo there. boiler. This is the turbine. Happens quickly, so it's an adiabatic process. And then this is the condenser. We transfer the steam back to a liquid. So that's what a Carnot cycle would look like on a TS diagram. And this is an idealization of the steam power cycle. It tends out to, in practice, be a little bit different from that. And there's a few practical reasons why. First of all, it's very difficult to increase the pressure of a liquid-gas mixture. We can use a compressor for gases, and we can use a pump for liquids, but we really don't have a device that will increase both of those at the same time. It would be much easier if we let this completely condense, and then we could just pump on the water. That's good news, because it's actually very difficult to sort of stop the condensation partway through. How would you practically do that? The final problem with this is that in this region right here, if this were to pass through the turbine, this would be a mixture of liquid and gas, right? This is in the mixed phase region. And the high pressure water will actually seriously damage the turbine blades. So it's much better if everything remains in the gaseous state when you do that adiabatic expansion and you do work in the turbine producing the electricity. So we modify this cycle. First of all, we let the condensation happen completely. Then we pump up the pressure. Then we let the boiler heat it up. And we actually enter over here into the region of superheated steam. And then we run it through the turbine. Over here, it's what we call dry steam. There's no liquid content. And then we condense it back and repeat. This is known as the Rankine cycle. So those three problems that I just mentioned are detailed right here. So first of all, you can't just stop the condensation process halfway through. You've got to actually take it all the way. Secondly, it's very difficult to pump a liquid gas mixture. It's much easier just to pump the water. And then third, you don't want liquid going through your turbine because it'll damage the blades. So here then is the modified cycle. The Carnot cycle would have been right here, that box in the TS plane, but this is what we'll actually do. So we'll actually start off, we'll pump up our water to a high pressure, then that water will enter the boiler where it will absorb energy, it will heat up, it will start to vaporize into steam. Here it's completely vaporized into steam. Then we'll superheat the steam up to this point. So boiler was from here to here. Then over here, we'll run it through the turbine and produce electricity. And then we'll run it through the condenser. So we'll call this point 1, point 2, point 3, and point 4 for the point of view of our further analysis. Now, when we get to the power plant, we're going to be interested in what are the temperature and pressures at each one of those points, 1, 2, 3, and 4. Because when you know that, you can use what are known as steam tables to figure out how much energy was associated with the pumping, how much energy was absorbed through the boiler, how much energy was released through the turbine, and then through the condenser. And so that will be this diagram. And this, of course, I should say, this is known as the Rankine cycle now. It's not a Carnot cycle anymore. It's a slightly modified Carnot cycle to deal with the practical issues that you encounter when you're using steam as a working fluid. So pause, and then a key concept for power generation and the calculations that we'll do. So here we are, back with our 4 components. Here's the pump up the pressure, goes through the boiler, absorbs lots of heat energy, gets really hot, then it goes through the turbine, makes electricity, and then the steam gets condensed back to water. A key concept in that, all that is going to be the enthalpy, and this is in the next note package for the next unit, if you're looking for this. So enthalpy H is defined as the sum of the internal energy plus pressure times volume. Now the reason this is useful is the following. Enthalpy includes both the internal energy and the internal PV work, that we're going to call it, done by one part of the gas on another part of the gas. And as a result, it represents the total energy that's needed, or the total energy that we can get from a thermodynamic process. For instance, if we were to start with a higher energy, internal energy state and end with a lower, then we have potentially released 3 units of internal energy. However, our working fluid, our gas, has done 1 unit of work on itself. The PV work is in, whereas the internal energy is out. So the net result of this process is actually less than just the internal energy change, because the gas did some work on itself. Thus, instead of releasing 3 units of energy to the environment, we're actually only releasing 2 units of energy. Now this is germane to power plants because if we consider a certain volume of gas that's actually in, say, the turbine, in that control volume. So here, let's say this is the base. So we've got a volume of steam here in the turbine, but there is, of course, steam flowing in and flowing out all the time. So let's look at those 2 other elements of gas. And these 2 elements of gas, this one's going to do work on the volume here in the turbine. And then the volume in the turbine is going to do work on this one, moving it out of the way. So this side here is side 1, or initial, and this is point 2, or final, because the flow is going to the right in this diagram. Now on the initial side, on the 1 side, the pressure is relatively constant, so it just comes out. And then we add up dV. Well, our volume here is actually decreasing because this is pushing in, and therefore the volume change, the dV, is just negative V1. So overall it's positive, which makes sense because we said work was being done on our gas here. Work is being in. Work is in because we're pushing on our gas in our turbine. At the same time, this gas is pushing this one out of the way. This is going to be work out. This process happens at pressure 2. And the change in volume is just V2, and it's positive. This is actually moving this out of the way and making more space for itself. So there's an increase in volume for this gas. And therefore that is work out. So if we put that into the first law of thermodynamics, we get delta U, the internal energy changes if there's Q or if there's work done. But we're really saying there's 2 types of work here. There's this internal work, which is the gas doing work on itself. 1 bit of gas pushing on another. And then there's the external work of actually spinning the turbine. Now we've seen that this internal work is expressible in terms of PV. So we had a term like P1 V1 minus P2 V2. Well, that's exactly negative PV, because delta means final minus initial. And so this is final and this is initial. And then with the minus sign, you get exactly this term. So the change in internal energy is dependent on the heat flow in or out, the internal work done, which is negative delta PV, and then external work done on a turbine or on a piston, something like that. So This internal work then, we're going to lump it over here on this side with the internal energy. And then we realize that we've actually got our old friend enthalpy here. And we see that this is a very useful concept when we're dealing with power plants, because it means that we really don't have to worry about the internal work, since that's already included within enthalpy. The only thing that's going to change the enthalpy is either heat flow in or out of the gas and external work, such as spinning a turbine. So the delta PV work, we say, is work internal. It's one part of the gas doing work on the other. So enthalpy is going to be a constant if there's only internal work done. Because if there's only internal work done, that means there's no external work and there's no heat flow into the system. The enthalpy is going to change if we have heat flow into the system or external work done, and the change in enthalpy is exactly equal to the heat flow in plus the external work. So this makes it a tremendously useful for studying the steam power plant that we're about to go and visit. And so what we're going to do is there's actually a standard table of enthalpies for steam. Once you know the temperature and the pressure, you can actually just look up the enthalpy. And once we know the enthalpies at various steps in this process, so at point 1, we're going to find enthalpy 1. At point 2, we're going to find enthalpy 2. At point 3, we'll know what the enthalpy is at that point, and so on and so on. Then you can find the delta H for each step. And then ultimately you can find the efficiency of the cycle. This is what our task is going to be.